Now that we know how to graph quadratics, we can use graphs of the quadratics to solve the quadratics. The same is true of our linear functions. If we take the linear function, let's try 4x minus 8 equals 0. We could solve it algebraically. It's actually quite simple, and get x equals 2. Or we could take the corresponding function and graph that. We'd begin at -8, rise 4, run 1. And then we could look at the graph, and where the graph crosses the x-axis will be our solution, 2. The same thing is going to happen when we do quadratic functions. If we graph it, the places where it crosses the x-axis are going to be the solutions to this equation. In fact, if you scroll up in your notes, it's in one of the key concepts here already. Notice where it crosses the x-axis. Those are going to be the roots, the zeros, or the solutions to this quadratic. So let's practice. Let's begin by graphing. You know, I always like to start with my vertex. -b over 2a would be the opposite of -3 over 2 times 1. So 3/2 is the first part of our vertex. And when we put that back through our function, so now I'm going to calculate it. Just rub in 3/2. That for x, and then I'll type the function x squared minus 3x minus 4 negative 6.25. So 3/2 results in negative 6.25. 1 1/2 means go down 6 1/4. Not the easiest point to plot, but we can get some other nice points on our graph. Let's try the point 1. 1 minus 3 is -2. Minus 4 would be -6. Buy one, get one free. We also have the point 2, -6. How about 0? The y-intercept is c, 0, -4. Buy one, get one free. If I go 1 1/2 spaces to get to the axis of symmetry, which I could draw, by the way. We can always have our axis of symmetry on our graph if that helps you. 1 1/2 spaces to the right past would be right here at the point 3, -4. And we can connect these points. And we see that we have x-intercepts right here, which means that when x equals -1 or 4, this function is true. And you can even check it. -1 squared is 1 plus 3, because -3 times -1, take away 4 equals 0. Or I could sub in 4. 4 squared is 16. Take away 12, take away 4 is also 0. So we found the solution by graphing. Not all functions will be easy to do that with. They don't always line up very nice and neat on our x-axis. But something before we get too far ahead of ourselves is to consider this key concept. The graph of a quadratic can cross the x-axis twice, just like we just saw, and have two solutions. Sometimes, though, it's not going to cross twice, it's just going to touch once. And when that happens, we have one solution. And sometimes it's not going to even cross at all, in which case we would end up with no solution. Those are our three options when we're solving quadratic equations. Looking at this graph here, you can see that it starts off where the y values are positive, and then we cross over and we are negative. We are below 0 until we get to here and we cross over again and it's positive. If you're looking at a table of values, you can see that when we cross from the positive y values over to where the values become negative and back to positive, that's where the intercepts occur. There's an intercept right here. I can't tell exactly what it is because it's in between integer coordinates. It's somewhere between 0 and 1. And then there's another one right here. Can't tell exactly where it is. It's past 5, but it's not quite to 6. It's somewhere between 5 and 6. Sometimes we can't find the exact roots by graphing, and the best thing to do is to estimate between consecutive integers. These are integers 0, 1, 5, 6. Those are consecutive integers, and we can say with confidence that the zeros would occur somewhere between those. Scrolling back up in our notes, the problems at the beginning, we did not find the zeros. But on our first example here, I know there's one between 0 and 1, and I know there's another one between 3 and 4. That's where my zeros would occur. If I need exact zeros, or estimated zeros rounded to the nearest hundredth maybe, or thousandth, I can take this function and graph it with graphing technology like Desmos or my TI. I'm going to show you both ways. If we start with the TI, clear out what's in our calculator. In y1, I'm going to type 3x squared minus 12x plus 6. Now, to figure out where it crosses, I'm going to press second trace. I want the 0, which is option 2. I want my little flashing cursor or spider to be before where the graph crosses. So right up here, because this is where the 0 is, I want it before as I go from left to right. So I hit enter. Then I move my cursor to the right, enter. And then the calculator says, would you like me to guess? And I say enter. And it tells me 0.586. So that's one of our zeros, 0.586, which sure enough is between 0 and 1. Then I could find the next one. Again, second trace, option 2. I want my cursor to be before where I think the 0 occurs, and after. And I guess, and I get 3.414, which is between 3 and 4, just like we thought it would be. What does this look like on Desmos? On Desmos, I'm just going to type 3x squared minus 12x plus 6, happens a little faster. I also simply need to hover over these points, and it tells me right away what the values are. So using Desmos can be faster, but using the TI is useful to know because that's all you will have access to for an ACT or an SAT. All right, let's take a look at a couple more word problems. A golfer hits a ball from an elevated tree box 200 feet above the fairway. The ball's height above the fairway is modeled by this function, where t is the time in seconds after it is hit. How long will it take for the ball to reach the fairway? These type of trajectory problems are very, very common word problems in the realm of quadratics. It's really easy to model it. Let me show you exactly what I mean. I'm going to start by drawing just the first quadrant. You might say, well, why are we only interested in the first quadrant? Well, we're dealing with two things. T is the time, and the ball's height. Both of these variables cannot be negative. This is our time, and this is our height. Notice, I'm just drawing a sketch of this, that the ball starts, when time is 0 right here, it starts 200 feet up in the air. The person's standing like on a platform. And they hit the ball and it goes up into the air, and over time, the ball eventually starts to come down and hit the ground. This point right here is going to be our vertex still, and it's going to have the x value in time, and it's going to have the y value as the maximum height. This point right over here is going to be one of our x-intercepts. In fact, it's going to be our only x-intercept. This is when the height is 0. The ball is on the ground, and this happens when x is this value. So it's asking us, how long will it take the ball to reach the fairway? How much time has to pass before the ball hits the ground? That means we're looking for this point. We want to know, when is the height 0? When is this 0? In other words, we're taking this equation and solving it. So if we graph this equation using Desmos, negative 16x squared plus 28x plus 200, you can see that the graph looks a little different than my sketch, but it starts at 200 and it goes up, and then it comes back down and eventually crosses right here. And this is the point 4.5170. So what does that mean? After 4.517 seconds, the ball hits the fairway. Now sometimes it'll ask, what's the highest the ball gets from the ground? Well, the highest is going to be the highest height. That happens at the y value of our vertex. So looking back at our graph, where's our vertex? Zoom out a little bit. Scroll up till we can find our vertex. You know, it's pretty high up. There it is. And if we just touch on it, it'll tell us that the height. Now, which one of these two numbers is height? Recall, x is the time, so after not even a full second, the ball gets to a maximum height. It goes up 12 feet and it immediately starts to come back down. So it gets to a maximum height of 212.25. And again, what was the height when the ball was hit? 200. That's our y-intercept.